just in general. Okay. Well, the plan here for today, if you guys don't have questions from homeworks, is we're just going to kind of burn through 15.2 here. So I don't have a ton. It's basically just like a couple of mathematical models and then doing some story problem application with it. So I don't want to, like a third of the class absent. I'm not going to go blazing through 80 minutes worth of stuff. But we'll do a little bit of stuff here. So remember, what we've been working on has been these exponential and logistic functions. The logistic functions, I'm never going to ask you to be able to write your own equation for one of those. They would be given to you in a problem and you just have to use it. But exponential stuff we will. So to help kind of create a framework of like how to write your exponential equation from something other than like, here's some points and I'm telling you it's exponential. We're going to look at a couple of different common presentations. So the first is this kind of exponential population model. Now, I want to be clear here, when we say population, we don't necessarily mean like living things, right? It could be living things, but it could be like, we could be talking about, like the, like demand for an item, like something like, it doesn't have to be a living organism. We call it population, but it doesn't mean like people or animals or something, although it could be. So when we talk about the population P, and it's changing at a constant percent or a constant rate, so that's our R. Notice in the formula that R is divided by 100. That's just me building into the formula, converting that percentage into a decimal. Okay? If you do that by, like, just in your head and rewrite 7% as 0.07, don't divide by 100. The 100 is there to divide, is converting the percentage into a decimal. That's all that's there for. Is everybody okay? And then the T is the unit of time. So keep in mind that sometimes that is not a regular unit. Like if you're talking about some population of like a computer virus that like doubles in size every 32 minutes or something, then like 1 T is like 32 minutes or something. Like it might be weird like that. And then the initial amount, like your starting population, is just that P0. So I can tell when a population model is going to be growth or decay, because this piece is like my B, right? So if R is positive, 1 plus R over 100 will be greater than 1. That's going to imply that we have growth. If R is negative, 1 plus R over 100 is going to be less than 1. That's going to imply that we have decay. Does everybody feel okay with that notion? Okay. So let's go ahead and do a couple examples here, kind of run through looking at this. So the first example 7 says indicate whether the following population models are growth or decay, and then find that constant rate of growth or decay. So as we pointed out before, the piece with the t attached to it, that's like our value for b, right? Maybe I'll highlight so that the t doesn't get like overwritten. And I know that is going to be, then we can say that 0.0384 is equal to 1 plus r over 100. So if I want to solve for r, what would I want to do first? Well, you could clear fractions first. I would just subtract the 1 and then multiply by 100, right? But you can multiply by 100 and then subtract 100. That's fine too. Either way is going to get you this to the same spot. So when I do that, I get 3.84%. And since that's a positive value, that's going to be growth. I could have also decided it was growth just from the beginning because I noticed the b value there is greater than 1. That would be fine too. If I look at the next example, so there's my b. So I can say that 0.9867 is equal to 1 plus r over 100. So when I when I subtract 1 from both sides, then multiply by 100, I'm going to get that r is negative 1.33%, which tells me that's going to be decay. Or I could have observed that it was going to be decay from the beginning just by seeing that the number was less than 1. Either way of thinking about that is fine. Does everybody feel okay with what we did there? Pretty easy, right? You just have to recognize what it is you're looking at. Okay. Oops, I forgot one example. That's okay. We'll just drop it in here. All right. It says determine the population model with an initial value of 15, increasing at a constant rate of 6% per year. So I want a population model, so I'm going to be using that model we were looking at the start of class. So that's what I'm writing. So I need to fill in to this population model. I need a P naught, and then I need an R. Well, and then potentially I have to maybe monkey around with my T. We'll decide there in a moment what we want to do about that. So let's read in our problem. So it says the initial amount is 15, so that's my P naught. My constant rate of increase or growth is 6%. Now I know that that 6% is a positive 6% because of what other word? The increasing, right? If that said decreasing, then it would be a negative 6 for my R. Is everybody okay there? And then the part of this that has to do with the T is that it's happening every year. So if I make T equal to years, I would write this that way. And if I simplify that piece inside the parenthesis, is everybody okay with that? Now I want to point out to you that I chose to represent t in years. Ugh, this stupid thing. If I had, say, done t in like centuries, what would I need to do here to adjust if the 6% is happening every year? How much of a century is 1 year? 1/100th, right? So if I did that, now I don't know why I would want to do it that way, but like 1 year is 1/100th of a century, right? So I would just need to change t appropriately to match the unit that I'm using there, right? Does everybody feel okay with that? Now here, because it's every year, I would see no reason not to just use years. But if we look at the next example, it reads almost identical, right? It's like, okay, well, initial population of 15, increasing, constant rate of 6%. The only difference is that happens now every 6 months instead of every year. So I could write it this way. I can say P of t is just equal to the same thing as before, but this time where t is like a 6-month interval. So when t is equal to 1, that's been 6 months. When t is equal to 2, that's been 12 months. So I have to make sure I understand what I'm writing. Or if I said, okay, I don't like that. What if I have t equal to just years? Let's say 1 year intervals. How many 6-month intervals are in 1 year? 2, right? So I'd have to say, okay, well then that should be a 2t. Or maybe I say, well, what if I just want t to be months? That might be a thing we would want to do. In that case, how many how much of an interval is, or how much of 6 months is 1 month? It's like 1/6, right? And any of these answers is correct. They will all give you the correct answer, but you have to be mindful of like, what is our unit for t, right? All of these answers would be correct. You could answer any further questions after you've written the model using any of these models, but you might have to do some cleanup at the end with like, oh, I got 6.2 for t. Like, is that 6.2 years, as in the blue? Is that 6.2 months if I wrote it in the green? Is that 6.2 6-month intervals? Or like 36 and a quarter, 38-ish months or something? Like, you have to be mindful of like, what did you pick for your t? Everybody's okay with that? So sometimes there'll be some unpacking at the end. Let's look at an example where now we do that. We'll write our model and then solve it for a value and have to do the unpacking part at the end to make sure that we're answering our question correctly. All right, it says, suppose a colony of 120 bacteria is put into a petri dish and the culture doubles every 3 hours. Predict how long it will take for there to be 400,000 bacteria. So this guy is like my initial amount. And I see the time while it's happening, it doubles every 3 hours. But where's the percentage? Where I don't see a number for the percentage. Did they hide it with a word? What is the word? Doubles. That's correct. What percentage does double imply? 200%? No. So if we had $100 and we had 200% change on that, that $100 would turn into $300 because you would have gained 2 times your $100. Now you'd have $300 in there, right? That's not doubling, but you're close, right? What should R be? So if R is 300, then we would end up with 4, like 400. That's not what we want. You're going the wrong way, right? R is 100. So if I have 100% growth, my $100 grows into another $100, giving me 200 total. That's what I want. Okay, so double R means 100. Everybody's okay with that? Think about, like if you're shopping, think about a sale. If something is 50% off, it's like half its price. If it's 100% off, it's free. It is all of the monies, right? If it had a 100% price increase, it would be twice as expensive as it was before, right? Just trying to connect the language to the common sense things that we encounter every day to be like, okay, yep, I'm good with why that has to be that way. All right, so let's start writing our function. Now, what do we want our time, what our t measurement should be in terms of what unit, do you think? Again, it doesn't really matter. We just need to make sure that we're picking something and being careful about it. So I think the t, what unit of time though? Hours. I would just do it in hours. Right? You could do it in 3-hour segments, but then you're going to have to take your final answer and multiply it by 3 at the end. I'm going to be bad at remembering to do that. I would rather fix my equation so that the answer spits out. I just attach the same unit to it and I'm done. But you could do it in 3-hour intervals. That would be okay, but you'd have to make sure you adjust your answer at the end. I would opt for, I want to write this in a way I don't have any adjusting to do. So when t is equal to 1, how much of a 3-hour interval have I completed? 1/3, right? So this should be like t over 3. Okay? Because I've done 1/3 of that 3-hour interval when t is equal to 1 hour. Does that make sense? Now, would be fine if I did t in 3-hour intervals, but I would just have to make sure that I remember to adjust my answer at the end. So when I simplify this down, which you don't really need to do because this is just going to go into our calculator in a minute. But I'm going to opt for doing that because it makes typing into the calculator a little simpler. That's what's going into my calculator. Now, I need to solve that when P of t is equal to 400,000. So I just completed step 1, where I've written my equation. And now I'm going to complete step 2, which is solving my equation. We still don't have the algebraic tools yet to solve these things. So to solve this, it's just going to go into my calculator, where I'm going to do an intersection. Everybody's okay? Just like we did last time. So I have 15 times 2 to the x over 3, and then 400,000, 2, 3, 4, 5. And I'm going to check my window here. So the x's are representing hours. So don't really, we're starting at 120. Every 3 hours it doubles. So like 3 hours, I'm going to have 240. And then 6 hours, I'll have like 480. And in 9 hours, I'll have 960. So this is going to take a while, right? You guys get the idea? So I don't know. I think probably up to 100 is probably reasonable that it would hit between then, but I'm not really sure. I'm just going to guess that, and we'll see how, if we have to readjust, we might have to readjust. The y's are going to be based on the number of bacteria, right? So the least amount of bacteria I'll ever have is the starting amount. And the most I need to have is 400,000. So I want to make sure I can see the 400,000, so I'm going to pick a y max bigger than that. And I don't want to type in 120. I'm just going to do 0 because it's quite frankly close enough. So I'll do 0 to like 500,000. Everybody's okay with that reasoning? Let's hit graph. So there's my, whoa, doubling is fast. So there we go. Second trace, intersect command, enter, enter, enter. And I get 44.1. Is that 15 times? Oh, 15. What did I do 15 for? How come nobody yelled at me that I wrote 15 here? What should the 15 be? Yeah, 120. Like, what are you doing, Mr. Kulik? You're still on the previous problem. Great, googly moogly. Yes. Let's try that again. I was like, that's not what I had on my paper. Okay. Let's do that one more time. Got there a little faster, it looks like. So we get 35.1. Everybody feel okay there? Just to show you that if we did it as Will had suggested and just did it with 3-hour intervals, so we would have just 2 to the x. We do the same thing. And find that intersection. And we'd have 11.7. But remember, I have to take that answer then and multiply it by 3 to get the total number of hours. Which is the same 35.1 that we got here. So it's purely a matter of preference on that, but you have to be aware of what's going on. You know what I'm saying? All right. I have one more kind of situation to deal with. This situation is called radioactive decay. Those of you that have been in a chemistry class or an earth science class are probably familiar with this concept. But the idea is that the atoms in a radioactive substance like change from a radioactive element to a less or not radioactive at all element by ejecting some particles from them over some unit of time. We measure how radioactive a substance is through what's called a half-life, and that's the amount of time it takes that particular substance to, like, half of it to change into its, like, more stable version of itself. So this is still can be done using this model where the R every single time is what is the R every single time going to be in a half-life situation? Half-life. What is the R going to be? Remember, it's got to be a percentage, not 25.
42.
Not 42.
50.
You're close, but not 50.
54.
Not
39.
No.
62.
It's negative 50. Because what is this?
I was not going to.
It's decay, right?
I was really.
Everybody's okay with that? Shh. And really, the T, we're going to always adjust because we don't want T to be just the number of half-lives, right? We want it to be like in hours or minutes or days or whatever the half-life is measured in. So it'd always be divided by the length of that half-life. And then the unit of that length will be whatever T is, right? If the half-life's measured in days, then it'll be days. If the half-life's measured in hours, then it'll be hours. Or if it's in picoseconds, it'll be in picoseconds. If you have something like synthetic radioactive element that exists for just like a fraction of a second inside a particle collider or something. All right. Let's do some examples here. Suppose the half-life of a certain radioactive substance is 35 days, and that you have 10 grams of the substance initially. Find the time it would take for only 1 gram to be remaining. Okay? Well, I know that that's my initial amount. I know that my R, because we're talking about half-lives, is negative 50%. And then the piece that's going to tell me about my T, I'm going to have T in days. So I'm going to have T over 35 in my problem. Everybody okay with that setup? So I'm going to do 1, and then I'll just simplify that down And that's what's going into my calculator then. And these half-life problems are nice because picking a window is no longer going to be guesswork. I'll explain in a second. So there's my function. There's 1. So my window, well, let's think about our x's. A half-life is 35 days, right? So after 35 days, I have 5. After 70 days, I have 2.5. After 105, I have 1 1/4. After 140 days, I'm going to be less than 1, right? So I'll go 0 to 140 for my x, because I know that I'll hit my answer inside of there. Everybody feel good there? Now for my y's, the biggest amount of stuff I'm ever going to have is the start at 10, right? And what's the least amount of stuff I'm ever going to have? 0, when it's all gone, when it's all decayed away, right? Every decay problem, the minimum's going to be 0 and the max is going to be the start. Oh, well, that's really easy to pick a window for. So let's hit graph. Here's my decay function. There's y equals 1. I can see the intersection right there. Second trace, intersect command, enter, enter, enter. And I get 116.3. And if you had done this without the t over 35, if you had just done t, whatever your answer is, you would have just had to then multiply by 35 because you would have found the number of half-lives. Feel good so far? Very similar to what you've been doing, right? Not a big leap forward. You're just writing your equation in a new way rather than building it off of 2 points. All right. It says you start a bunny petting zoo. That sounds lovely. You determine the population of bunnies on your farm can be modeled by the equation B of t equals yada, 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 where t is measured in years. How many bunnies do you have initially? Well, what time is initially?
0.
Yeah. So I'm just going to do b of 0. So e to the 0 is 1. 1 times 99 is 99. 1 plus 99 is 100. So initially I have 8 cute little bunnies. What is the maximum sustainable population of bunnies on my farm? If we look at our function, you should recognize the form of this. What type of function is this? It's a logistic, right? Remember, a logistic function has 2 horizontal asymptotes. One of them is always at 0. The other is at y equals c, where that c is just the numerator of the fraction. That is my maximum sustainable population. That's easy. And then it asks, how long will it take to have 500 bunnies? Well, I just need to solve b of t equal to 500. Calculator time it is. So I'm going to use the fraction command. We have 800 divided by 1 plus 99 e to the negative 0.5x and then 500. I'll reset my window here. I don't really know how long this is going to take per se. So maybe I'll do like, I don't know, like 25 years or something. Sure. Oops. And then my y's, well, my y, I start out with 8. I want to go to at least 500. Well, I'll use my asymptotes, 0 and 800. That'll be good. Let's do that. That should probably be good. Let's hit graph and see what we get here. Ooh, boy. That happened fast. Right, I had 25 as my x. Inside of 10 years, just over 10 years, I'm going to have 500 bunnies. That's a big operation all of a sudden. Everybody that comes to my petting zoo, take a bunny home. Buy one ticket, get one bunny. Got to start clearing out the inventory. Yes, Joey. Sure. What do you guys think on this? No big deal, I hope, right? Okay. So you guys should be able to do then 17 to 36. So that's not going to be due this Sunday. It'll be due the following Sunday. The only thing due this Sunday is the 1 through 16 from 5.1. This 17 through 36 will be due the following Sunday. Yes, Bella. It's not been, I haven't assigned it yet. We haven't gotten through enough stuff to do it. I made it and put a due date on it or whatever, but I haven't assigned it yet. Yes, Ella. Sure. What do you guys think? Feel good?
Yeah.
Okie dokie. We're done for today. Yay.